So picking up where we left off now, next week you're going to have, Tuesday in lab, you're going to have your test. Remember, it's going to be 150 multiple choice questions. So we'll go over, hopefully we'll finish the chapter either today or at least Thursday, and I'll go over and tell you what you need to know. There's only a little bit of math, So ionization was pulling off an electron. Kind of the opposite of that is electron affinity. That's energy released when an atom in the gas phase accepts an electron. So you see chlorine in the gas accepting an electron, and it releases 349 kilojoules per mole. And here you can see some of the electron affinities. That table's in your book. What are some trends? Because we're talking about trends here. And again, usually as you go left to right, the electron affinity goes up, left to right across a row. And as usually as you go from top to bottom, it decreases. Because as you go from left to right, what happens is you're getting a more effective nuclear charge because you're adding protons. But in that row, you're not adding any more valence shells. All the electrons are still going to be in the same valence shell. So they're still going to be the same distance from the nucleus, but you're increasing the charge on the nucleus. So because you're getting a stronger positive charge, it's easier to pull in the electron. And again, just like with ionization energies, there's some anomalies, as they call them. So as you go from group 1A compared to group 2A, see 1A, you have that open lower shell, the S subshell. You can still put an electron in there. Where in 2A, the S subshell is filled, so you have to go to the P subshell. The P subshell is higher energy. So it's easier to put the electron into the 1S than it is into the P. Or the 2S and the 2P, because there's no P in the 1. Between group 4A and 5A, 4A has an empty box, so to speak, in the p orbital, whereas 5A, you have to double up. So 5A is like trying to stick that extra cap in there. It's harder to do. So looking at, we're talking about EA1, so the first electron, aluminum or silicon. So you look, again, aluminum and silicon, we're going 3A and 4A. And silicon or phosphorus, we're going 4A and 5A. So again, writing out the orbital diagrams, there's aluminum, there's silicon, there's phosphorus. We see both aluminum and silicon have an open box. But silicon has one more proton, because it's to the right of aluminum. So it's going to have a higher nuclear charge, higher positive charge. So it's going to attract the electron easier. So silicon should have a higher EA than aluminum. But now you look at phosphorus compared to silicon. Silicon has the empty box, so you can stick an electron in there fairly easily. Whereas phosphorus, all the boxes are full. So it's harder to stick the electron into the phosphorus box. So silicon should have a higher electron affinity than phosphorus. So silicon is greater than aluminum because it's to the right. But it's also greater than phosphorus because phosphorus is to the right of silicon, but all the p orbitals already have an electron, so you have to pair with phosphorus. It's easier to get the electron in silicon than phosphorus. So even though the trend generally increases going left to right, there are those exceptions. So if you had that question on the test, I would look at that chart. You had the little dots. Just label with the little dots. And you'd be able to tell which one's greater than the other. Let's talk about metals. Okay, this may come as a surprise to you. Metals happen to be shiny, lustrous, and malleable. Everybody knows what malleable means? No, it means you can pound it like crazy. You can take gold and pound it so thin, it's only a few molecules thick. We call that gold leaf. So if you go out and ever get to Europe, and some of the churches in that, or actually I think the dome in the Capitol is covered in gold leaf. You can put that on there so it looks like gold. It is gold. Oh, real cheap jewelry. You can scratch the gold right off if it's real thin. All right, they're good conductors of heat and electricity. They have low ionization energy, so they lose their electrons easily and become cations. They form ionic compounds with chlorine, metal chlorides, and they form basic ionic compounds with oxygen, metal oxides. Nonmetals vary in color and are usually not shiny in appearance. They're brittle rather than malleable. You cannot take a charcoal briquette and try to pound it into a sheet. You're not going to be too successful. It'll splatter all over the place. They're poor conductors of both heat and electricity, and they tend to form acidic molecular compounds with oxygen. And they have high electron affinity, so they want electrons, so they tend to become anions. So there's the metals and the nonmetals. Metalloids, somewhere in between. And metallic character increases from top to bottom in a group and decreases from left to right. So the most metallic character is the bottom left periodic table. Down where cesium is. Ions of the main group elements. Okay, here we go. If you look at helium, it's 1s2. So it's in column 8. It's the only one that's 1s2. All the rest of them are ns2 and p6. So 2s2, 2p6, 3s2, 3p6. So you go right down column 8. They all end in s2, p6. 8 valence electrons. So they're extraordinarily stable. So that's the key to the whole periodic table is column 8. Everything wants to be like column 8. So it's going to react. Remember we said reactions occur with the outermost valence electrons. They're going to occur so that the elements that react end up with those magical 8 electrons. And species with identical electron configurations are called isoelectronic. Is that all right, isoelectronic? I think so in this class. So, argon, how many electrons?
Balance
Total electrons? 18. So I assume you can all do the electron configuration for argon, 1s2, 2s2, 2p6. All right. Chlorine, how many electrons? 7. Chloride, Cl minus, how many electrons? 18. We added a minus. Notice chloride and argon have the same number of electrons. So if I do the electron configuration for chloride, what's it going to look like? argon. So those are called isoelectronic. If I look at the potassium ion, K plus, how many electrons? No. K is 19. If I have a plus, I have to lose an electron. 18. So all three of these are isoelectronic with each other. That's what I have to do to figure it out, is take the ion. If it's plus, you subtract that number of electrons. If it's minus, you add that number of electrons. And if you get the same number of electrons with whatever else you're looking at, they're isoelectronic with each other. So you can see sodium, when we go to, there's its electron configuration, N3S1. If we take that electron off and give you sodium plus, we get 1s2, 2s2, 2p6, which is identical with neon, 10 electrons. Chlorine ends in 3s2, 3p5. If it gains an electron, it ends up to 3s2, 3p6, the same number, same electron configuration as argon. So that would be the shortcut to write their electron configurations. Na plus would be neon, Cl minus would be argon. So let's look at these, N3 minus. And what we got here, Ba2 plus. And lastly, Be2 plus. So N3 minus, how many electrons are we dealing with? 10. Okay. Nitrogen is 7, and we're adding 3 minuses. Ba2 plus, how many are we dealing with? Are you sure? Is it 54? 54, yes. 54. And Be2 plus, how many are we dealing with? 2. So now if we look up those electrons on the periodic table, N3 is the same as neon. Ba2 plus is the same as xenon. Princess Warrior. No, that was xenon. Okay. And Be2 plus is the same as helium. There. That's as hard as it gets. Oh no, you can make it harder. Okay, I will. All right.
What we just did, what was that called again?
Isoelectronic. So if you look at iron, there is the electron configuration for iron. If we say iron plus 2, you'd say, okay, I'm going to take 2 electrons. I'm going to take them off the 2d. So it'd be 4s2, 3d4. Now, that's not the way it works. When you lose electrons, it comes from the highest quantum number. So here's the highest quantum number is 4. So you lose 2 electrons from 4. So 4s2 minus 2, you just do away with 4s. So iron, 2 plus is argon, 3d6. Huh? Well, you just got to remember when you take the electrons, they come from the highest quantum number first. Okay, so, oh, by the way, doing electron configurations, people were asking me, in this case, iron 4s2, 3d6. Well, if I put down argon 3d6, 4s2, because that's how it shows in a little chart in your book. A lot of people do it increasing quantum numbers. 4s2, 3d6 is actually how it builds. 4s2 is higher energy. Either way is acceptable. There's a little note underneath that chart, student note, that says either way is acceptable. comparing ionic radius with atomic radius. Okay. If you gain or lose an electron, you form an ion. So the radius of the ion, let's compare it to the atom itself. So here we have, let's say, a sodium atom, 1s2, 2s2, 2p6, 3s1. So here we have a sodium atom. There's the nucleus on the 3s1 electron. Sodium's going to form Na+. So you get rid of me. I'm gone. So now the next electrons, the 2p's are over here. Closer or farther away? Closer. So as we lose electrons, the radius is going to get smaller. Okay, sounds easy. Let's go the other way. Let's form anions where I add electrons. Guess what happens when you add electrons? The radius of the ion becomes bigger because you're adding more stuff. Now, if you lose all the valence electrons, you get a significant decrease in size. So there's sodium. And you can see what its normal atomic radius is. And if you get rid of the electron in the third shell, so now you can see how it shrinks. It becomes a lot smaller. What would you think would happen okay, let's just do this. Of course, if we had magnesium, one has two, excuse me, 2p6, 3s2. So this is magnesium. If I make it 2+, remember I have 2 electrons, so I'm going to get rid of this outer one again, right? So is it going to become smaller or bigger than the Na+? You're saying same size. Because we got the same number of electrons, right? Na plus and Mg2 has the same number of electrons, but magnesium has another proton, so the nucleus is going to have a bigger charge. So guess what effect that's going to have on the electrons? It's going to pull them closer. You have a higher charge ratio. Oh, here we're going about a lot. Isoelectronic. Here, O2 minus, F minus, and neon are isoelectronic. Because O2 minus, they all have 10 electrons. So think about this. We have O2 minus, F minus, and E. So they all have 10 electrons. How many protons does oxygen have? 8. Well, no, always, because if you change protons, you change the element. So always going to have 8 protons. Fluorine has, next one in order, so it has 9. And neon has 10. So look at this ratio. They all have 10 electrons. What's attracting these 10 electrons here? 8 protons. What's attracting these 10 electrons? 9 protons. 10 protons. So which one has the biggest attraction? Neon. So which one's going to be the smallest? Neon. Then what's going to be the next smallest? Fluorine. Then what's going to be the next smallest? Or the largest? The oxygen. So there you go. There's the oxygen, the fluorine, and the neon. Even though you have the same number of electrons, you're increasing the number of protons, so it's going to pull it together. Right. So here's an example. You can see, let's look at sodium here. It goes from 186 for the atom to 102, slightly over half, which goes to the ion. Magnesium goes from 160 to 72. So it shrinks by more than half. We said, and look at aluminum, 153 to 54, almost 2/3, because you're getting more protons per electron. On the other side, you have phosphorus 3 minus, sulfur 2 minus, and chlorine 1 minus. So the effect is kind of reversed. But as you go to the anions, they get bigger. Okay, let's look at this series here. This would be a typical problem. See what's isoelectronic with each other. So, let me write them down. K plus, neon, argon, krypton, P3 minus, S2 minus, and Cl minus. First thing you do is see how many electrons. K plus has how many electrons? Pardon? 18. Neon, and argon, 18. Krypton, 32. 36. I'm sorry, 36. P3 minus. P3 minus. 18. S2 minus. Cl minus. All right, we see a bunch of them there have 18, so they're all isoelectronic. So I'm going to take away neon and krypton. These are all isoelectronic with each other. Then it says, arrange the ions in order of increasing radius. So argon's not an ion, so we're not going to worry about that. We're just going to do the ions. So now, they all have 18 electrons. How many protons does potassium have? 19. You didn't even have to look at a chart for that, because it's got to be one more than this. How many protons does phosphorus have? 15. How many protons does sulfur have? So, looking at this, which one has the highest positive to negative ratio? Potassium, K plus. So that's going to be the smallest one, because we got to do them at increasing, so let's start with the smallest one. So K plus is going to be the smallest. What's going to be next? Chlorine, because chlorine has 17 protons. Then sulfur, 2 minus, and then of course what's left is phosphorus, 3 minus. Okay, everybody see that?
And you would write them with the less than things too.
Well, if we're going in increasing order, yeah. Somebody told me one of the other classes, be careful on the test that you read the question. It says increasing, because I have people always listen to decreasing. Remember, the alligator's mouth always points to the largest. Huh? No. Oh, okay. So go on, and there we go. So that's fairly straightforward, he says. All you have to do is put the number of electrons and number of protons to see where the biggest attractions are. Biggest attractions, the smaller the radius. Oh. Went too far. We talked about elements of the same, oh, yes, I'm sorry. Okay.
How come AR isn't on the list?
Oh, because they asked for the ions. They asked what's the ion. AR is not an ion. AR is just a noble gas. If you were going to put AR in there, that would have went between potassium ion and chloride. That would be 18 and 18. I said that elements in the column have similar properties. Well, there's also the top member of each column has a diagonal relation with the next group down. So lithium has some properties that are similar to magnesium and beryllium with aluminum and boron with silicon. Because that has a similarity of charge densities of their cations. But if you look at hydrogen, 1s1, it shouldn't really be in column 1, but it's there because it has a 1s1. If you look at your periodic table, you see hydrogen's a different color than everything else in column 1. Because obviously hydrogen doesn't have properties like everything else in column 1. Everything else is solid. Hydrogen's a gas. So it actually belongs in a group by itself, but we stick it there because of the electron configuration. Group 1A elements have low ionization energy, so they form cations, a +1, real easily. They're so reactive, they're never found by themselves in nature. They're always found combined with something else. They react with water to produce hydrogen gas and the corresponding metal hydroxide. Oh, maybe in lab today while you're doing that, I'll get some sodium. We have sodium metal out, throw it in water and show you what happens. How's that doing that? So there's lithium, sodium. Sodium is usually kept under mineral oil because it reacts with moisture in the air and gives sodium oxide real easily. Potassium is always kept under a mineral. It'll start on fire and just pulling it out. And rubidium and cesium are kept in sealed tubes. Lithium forms lithium oxides. The other ones will form oxides or peroxides. Potassium, rubidium, and cesium also form what's called superoxides. The group 2A, the alkaline earths, are less reactive than the alkaline metals. So they tend to form 2+ ions. So there's, did I skip a page here? Did I go too far? No. So there's some examples of beryllium, well, magnesium. Everybody's seeing magnesium. They get properties of acids and bases. You looked at magnesium. There's calcium, strontium, and barium. They'll react with water, but it varies. Beryllium doesn't. Magnesium reacts slowly with steam. Calcium, strontium, and barium react vigorously with cold water. And the reactivity with oxygen also increases as you go down the column. 3A, boron is a metalloid. The others are metals. So boron is unreactive to both oxygen and water. Aluminum reacts with oxygen quite readily and forms aluminum oxide when exposed to air. So back in the days before vinyl siding houses, they had aluminum siding. Or aluminum awnings and that, and people would put it, be nice and shiny, and after 3 months it'd have this film on it. And they'd go out and wash it. So they'd wash it, clean it, get it all nice and shiny, and sure enough in 3 months it would be all filmy again. And they just keep repeating that process. But every time you clean off the aluminum oxide, more forms right after. Probably just as soon as you get done cleaning. And it actually forms a protective layer, so you might as well just leave it. It reacts with acid, especially hydrochloric acid, to form hydrogen gas. So if you look at videos on TV, you can find people who take Pepsi bottles, take aluminum foil, put it in there, and they go to get the works. Remember the works from the first day of safety? And I poured it on the egg, that's hydrochloric acid, and they throw it in there, cap the bottle. Well, it generates heat and hydrogen gas, and those two don't go together very well, and it explodes. Don't do that. That's considered by federal law as a weapon of mass destruction. You'll be arrested for a felony. Two students did that on a bus in Durham, and sure enough, that's what they were charged with, creating a weapon of mass destruction. Boron, aluminum, gallium has so low a melting point it'll melt in your hand. And indium. All right. Most of indium comes from Cleveland, Ohio. You all heard of the Cleveland Indians, right? Okay. They're in the World Series tonight. Okay. Sorry. Gray. Carbon is a nonmetal. Silicon and germanium are metalloids. Tin and lead are metals. Tin and lead will react with acid to give you the same reaction aluminum will. Some people use tin foil in the works. And you did that when you did properties of acid. You guys did properties of acid space, right? You had to collect the gas. Remember, you collected the hydrogen gas and lit the pop. Well, that's what happens in those reactions. So they can form both +2 and +4 oxidation states. Carbon and silicon, the more prominent, predominant +4. Tin, the +4 is slightly more stable, and in lead, the +2 is the more stable one. So the lead, you're losing the 6p2 electrons rather than all 4 of them there. So there's carbon, graphite, carbon, diamond, silicon, germanium, tin, and lead. There's also another form of carbon called Buckminster-Fuller. You know who Buckminster-Fuller was? He was an architect. You know he's famous for designing? Geodesic domes. Everybody knows what geodesic dome is? Epcot Center, in white. That's a geodesic dome. So, carbon, they discovered, can also crystallize as 60 carbon molecules arranged like a soccer ball. Think of a soccer ball. If you ever looked at a soccer ball, it's not perfectly round. It's like 5-sided panels that are all stitched together. Well, that's what a geodesic dome is. Very stable. So you actually design homes like that. Extremely stable homes, except really no way to hang a picture. No straight walls. And carbon can crystallize like that. If you heard of carbon nanotubes and that in manufacturing, super strong, stronger than steel. If we could make them en masse, we wouldn't have to use steel at all. Getting close to being able to mass produce them. And they named them after Buckminster, and they're called Buckminster-Fullerings, or buckyballs for short, because they make little balls. And graphite, everybody knows, is a lubricant. So the advantage of using graphite over silicon spray in that is it doesn't attract dirt. So people who do lubricate locks and that use graphite. Buy it at Home Depot, little bottle. Or if you got a stuck lock and you don't want to go buy a little bottle, what can you do? Use your pencil. That's graphite. Just rub it on the key, get some graphite on there, and stick it in there. Group 5A, nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, and bismuth is a metal. So you got all 3 categories in that column. Nitrogen, remember, is diatomic, so it's N2. Bunch of oxides for nitrogen, only one of which is a solid. And it has a tendency to accept 3 electrons to form the nitride, the N3- ion. And most metal nitrides are ionic. Phosphorus exists as P4 molecules. We have white or chains of P4 molecules, red. And there's 2 oxides for phosphorus. Let's see if we have pictures. We have pictures. So there's nitrogen, liquid nitrogen. Phosphorus, white phosphorus is kept under oil, and then there's the red phosphorus. Anybody know where you find red phosphorus? Matches. That's the red tip on matches. The white phosphorus is too reactive to be put there. Arsenic, do I need to even tell you about arsenic? Rat poison, or people poison if you're real good. One of my coworkers at GSK poisoned her husband with arsenic. Apparently got away with it. And apparently Napoleon was poisoned with arsenic too, because you find traces of it in his hair.
So where's the yellow phosphorus from? Is that just impurity? Or not phosphorus, no, I was thinking sulfur.
No, sulfur is yellow. Okay. I was going to say, I don't think I've heard of yellow phosphorus. Bismuth, where do we find bismuth? Pepto-Bismol. Group 6A, you have oxygen, sulfur, and selenium are nonmetals. Tellurium and polonium are metalloids. Oxygen is diatomic, colorless, odorless. Elemental sulfur and selenium exist as molecules S8 and Se8, and tellurium and polonium have complex structures. So oxygen tends to form 2-. Sulfur, selenium, tellurium also form 2-. And they form a large number of molecular compounds. There we go. There's a flask. Presumably there's oxygen in there, but I couldn't tell you because it's colorless, tasteless, and odorless, so it may be completely empty. Sulfur is a yellow powder. You can actually buy that in the drugstores. I still believe you can buy that. It's called florets, F-L-O-R-E-T-S, so sulfur. A lot of people use it for homeopathic medicine. They used to use it as an antibiotic to pour it in the wounds way back before there were antibiotics. Selenium and tellurium. The 7A are called the halogens. They're not found in nature by themselves. They're too reactive. High ionization energies, large electron affinities. They tend to form -1 ions. So they can form molecular compounds with themselves, and they exist diatomically. Fluorine, chlorine, bromine, and iodine all exist as F2, Cl2, Br2, I2. There they are. First flask supposedly has fluorine in it. Second one, chlorine, yellow gas. If you're here a couple weeks ago when we had the evacuation, when that truck was burning out back, if you learned the cloud, it was a nice yellow cloud. Chlorine gas. Don't want to breathe it. Bromine is a liquid, and iodine is a solid. It turns out we discovered, or you could take crystalline iodine, put it in a paper towel, soak it in concentrated ammonium hydroxide, take it out and let it dry. Now you have a compound called nitrogen triiodide. It's a contact explosive. Touch it, go bang, a little purple cloud. We used to have a lot of fun with that in graduate school. Make little pieces and put them behind somebody's chair and they'd roll back and go bang. But I digress. 8A, have all the noble gases. They exist as monoatomic species. They all have the S2P6 except for helium, which has S2. Greatly stable. Highest ionization energies, no electron affinity. Up until 1963, they were called the inert gases. You couldn't get them to react, but people found a way to get them to react, some of the heavier ones. So we have compounds like xenon tetrafluoride, xenon oxide tetrafluoride, krypton difluoride, and most recently HARF. I'm not sure what HARF is, but they made it. Yeah, fairly stable.
Even when you use this form? Or-
No. Outside of the fact that I like saying HARF. I don't know any other reason So there they are, and I showed you the ion discharge tubes, and you know they make the different colors for signs and that. And by mixing them, you can get different colors. Neon is the orange. So let's look at the transition. If you look at the group 1B, they have the same outer electron configuration as 1A. However, look at their first ionization energies. To pry off that electron takes a lot of energy. Group 1B elements are much less reactive. So if you think of those, copper, silver, and gold, we can find them uncombined in nature. Just about any night you can turn on some channel on TV and find somebody mining for gold somewhere. In Alaska, in the Bering Sea, in South America. You can take a pan and go out into the rivers in the North Carolina mountains and pan for gold and find it. Probably not enough to make a difference in your lifestyle, but you can find it. Thanks. And because they're so unreactive, we use those silver. Where do we use those? We use them in our body and fillings because they don't react. Sometimes we have plates put in your body if you break something. Now I use titanium, but they used to use gold screws and use gold in circuits because it doesn't react. If you used iron with moisture, it would rust. Not good for your circuits. So they use gold. A lot of times people would go and companies would go and they pick up old computers and that. All they do is put them in a big furnace, melt them down, everything burns except the gold, and they get the gold out. They make a lot of money that way. So here, we're looking at variation in properties. You see if sodium and magnesium oxides, they form basic solutions. Aluminum oxide forms amphoteric or ether. Phosphorus, the silicon, phosphorus, sulfur, and chlorine oxides form acidic solutions. And you can look, the melting points are all very high. So that's where that goes. And that was the end of chapter 7. See you chapter 7.